All right, hi folks. I thought I probably could have shown you this earlier, but there's one thing about basic vision that I think this is going to help you to understand the motion detector part. And there is a bunch of stuff that we're going to be talking about with schizophrenia involving motion, like velocity discrimination and stuff, and other things related to that. So I think it'll be good if you understand this motion detecting cell. Remember I drew on the board, there was like this cell that was hooked up to 3 retinal ganglion cells, and like it detected motion somehow. Maybe because it had different amounts of myelin connected to each one or something like that, different speeds at which their signals reached, the retinal ganglion cell signals reached the motion detector. Well, this is a image here in this video I'm going to show you of how, or it's a video of how the motion detector works. We're going to see a motion detector working, and it's pretty crazy. So let me back up to like right here. So what's happening here is that Hubel and Wiesel, this is Hubel and Wiesel, they've got a wire connected to a speaker, and the wire is going into the back of a cat's brain in his primary visual cortex, or her, I don't know if it's a male or female cat. But that's the deal. So you're going to hear the neuron firing. So let's listen. So what they're doing is they're flashing this light, and they're trying to, and then they're drawing on the white board where flashing the light causes the neuron to fire. So there's only certain spots where you flash the light and the neuron fires. If you split, I don't know if you can see my cursor, but if you shine the light way down here or something, you shine it up here, it doesn't respond. So they made this box. They're in the process of making this box to denote where the neuron fires. And the reason the box is like just in a place on the board is because remember the cat's head is clamped and he's unconscious. He's like sedated or whatever. So he's just kind of looking out into space. His eyes aren't moving, and so the light is bouncing off the board and hitting his retina in the same spot, you know, constantly over time. So they're able to draw out this receptive field. I'm trying to find the end of it. There it is. Okay. What they're noting now is that, holy cow, it's only when you move the dot leftward and up-ish that it fires. Go to the right, it doesn't fire. Go to the left, it fires. Try it again. Okay, now they're going to make it a line. Well, it doesn't like that. Now, WTF, why not? Oh, maybe it's because this line is so long, it's hitting the surround portion of the receptive field as well as the center. I bet they're going to shrink it again. We've got a fancy light thing they shine with. They shrink it enough, they're going to get it to fire again. A little bit. Okay. Okay, now it likes it. Now it's only hitting the center. Boom. Boom, boom, boom. Don't go too fast then. If they go too fast, it doesn't fire. If they go the wrong way, it doesn't fire. If they go the wrong angle, it doesn't fire. No, like that. Awesome. Okay, so that's a motion detector in action. This cell is some kind of motion detector. It likes stuff moving to the left and up. And yeah, that's how it works. And presumably that's because of something like I explained before, like the myelin connecting to the retinal ganglion cells that are responsible for that area of space or something. But I just wanted you to see it in action so you get a better sense of this whole this is called single cell recording. It's a very powerful technique for understanding what visual neurons do. You can use it in other parts of the brain too, but visual is what we've done the most with. All right, that's it for now.